Hello everyone and welcome to a presentation on protocols used in Internet of Things presented by myself Sritam and my partner Shreyas. As we all know that the Internet of Things is really transforming the way we interact with the world around us, and protocols have a major role to play in connecting and managing these billions of new devices around us. By 2020, it is estimated that the Internet of Things will grow to more than 27 billion connections across the globe, and we're just getting started. As Internet of Things comprises of billions of devices, and these devices communicate with each other, there must be standardized languages which these devices understand in order to communicate efficiently. In other words, there must be standardized protocols which these devices incorporate in order to efficiently communicate. So, protocols play an important role in the success of connecting these billions of devices around us in a reliable and secure way with minimum costs of production and deployment, along with longer battery life. Thus, protocols is an interesting area to explore when it comes to the domain of Internet of Things. We will start with LP1 as the first topic on our discussion about protocols. LP1 stands for Low Power Wide Area Networks. They connect objects wirelessly over miles for several years under battery at a very low cost. Why so? Because legacy wireless network technologies, unlike LP1, have been designed for very different purposes than connecting tens of billions of objects. LP1 supports large distances up to tens of kilometers. The key feature is that it supports long range but comes at a cost of reduced data rate. Only applications where data transmitted by sensors are very small in terms of bytes, but it needs to be transmitted to tens of kilometers will be benefited by LP1. A typical example of such an application is monitoring city garbage in real time and determining when they are full. These data of garbage bins travel several kilometers to reach to municipality offices. Accordingly, it enables city planners to optimize collection schedules based on where collection is actually needed, resulting in cleaner cities and cost savings through improved operational efficiencies. As explained earlier, LP1 is best suited for those applications where data rate is low, that is, the bandwidth requirements are really less, but transmission distance ranges are quite high. Other wireless communication protocols like Bluetooth, Zigbee, and others shown over here have higher bandwidth requirements, and thus the distance range is less. So the sweet spot for LP1 is lower bandwidth and higher range of communication. Many LP1 customers have previously tried to solve their wireless connection problems with mesh topology networks like Zigbee. They struggled with mesh network solutions because of high data rates, which resulted in lower link budgets. Link budgets, data rates, and receiver sensitivities will be covered in detail in the upcoming slides. So instead of a mesh topology network, most LP1 technologies rather use a star topology network. Repeaters can be used to fill in gaps in coverage, which for most applications is a good middle ground in terms of latency, reliability, and coverage. We will cover some of the basic concepts related to LP1. They are link budgets, data rates, and receiver sensitivities. Link budget is the measure of the amount of energy that is detected at the receiver side. Larger transmission power at transmitter side or higher sensitivity at receiver side can result in better link budget. Data rate and amount of energy per symbol are inversely proportional. Energy per bit is the main lever to change the possibility of a message being heard. To achieve this in LP1, the modulation rate and data rate are reduced to half, which results in putting twice as much energy into each symbol, thus increasing the overall link budget. So this is the key mechanism followed in LP1 to support larger distance of transmission with lower data rates. These principles of LP1 are implemented by many groups like Sigfox, LoRa, NB-IoT. Here is a brief summary of it. As you can see, the Sigfox is really low power, but the bandwidth is not as great as LoRa, and it's a bit open standard in that it does not restrict the use of confined hardware. It is open to any kind of hardware. Even in Arduino also it can be simulated, but LoRa, it restricts because it's not that open and it is only applicable in chips which are manufactured by the LoRa. And as we can see, the other factors are linked in the following way. But as you see, the deployments of NB-IoT is not as good as LoRa and Sigfox, because Sigfox and LoRa are widely distributed across France and major parts of Europe, but that is not the case with NB-IoT.
Hello friends, today we're going to discuss about the various IoT protocols and their suitability for resource constrained applications. Uh, IoT applications are operated in various networks, wireless networks, in a variety of constrained environments in terms of network conditions and limited hardware resources. Uh, for example, the demands of small wireless IoT networks or devices are outstripping battery lives. Thus, energy efficiency, performance, resource usage become important software design considerations. This this paper aims to provide certain guidelines to programmers when they go about choosing about uh, various IoT protocols for setting up network communication. Uh, the protocols we are going to be considering are constrained application protocol, message queuing telemetry protocol, MQTT sensor network, WebSocket, and TCP. Mm, In this paper, we aim to analyze how different protocols behave under different network conditions and with different message sizes. And IoT designers also need to be aware of how to go about choosing protocols for their applications. And our third aim is to uh, look for areas of improvement in performance and energy efficiency in designing newer emerging protocols. Before we compare IoT protocols, we can have a brief discussion of the protocols themselves. Firstly, we consider Constrained Application Protocol. It was designed by the IETF to connect devices with different constraints and specifications. As the name suggests, it's an application layer protocol. It overcomes the limitations of HTTP protocol, which is not suitable for constrained environments, and it's built upon UDP and it's built upon UDP and it's suitable for constrained networks and nodes. Uh, Next, we look at the message queuing telemetry transport protocol. It was designed by the Organization for the Advancement of Structured Standards. It's a lightweight protocol in the application level and is based on publish subscribe architecture. It's particularly suited for constrained devices in low bandwidth, latency, and unreliable networks. It attempts to ensure reliability and assurance of delivery of messages. It is based on TCP/IP. MQTT-SN is another protocol which is used in low bandwidth wireless environments, and unlike MQTT, it's based on UDP, and it's not suitable. It's not well supported as of now. And going to WebSocket, it is again designed by the IETF and provides two-way communication between browsers and servers based on TCP. It was originally designed to supersede HTTP, but nowadays it has gained importance in the domain of IoT communication protocols. Before we compare the various protocols, we need to look at the definitions of metrics by which they are compared. Performance. By performance, we mean the time needed to send messages and receive their acknowledgements. Energy efficiency means the time consumed for a given total energy consumed for a given execution time. Resource usage means the average Java heap usage measured every 500 milliseconds and the total CPU time. The experimental setup consists of one client and three servers located at different physical locations. These are local, Oregon, and Tokyo. The, the provided table looks at the various protocols and the libraries which are used in the experiment. The algorithm shows how each protocol is assessed in terms of performance, resource usage, and energy efficiency on the client side. The benchmark of application sends data to a remote server using different packet lengths ranging from 128 bytes to 1920 bytes. Looking at the performance metric, we can conclude that TCP and WebSocket protocols show the best performance across all benchmarks. MQTT SN shows the poorest result in the local and Oregon cases, while MQTT's performance increases with increasing packet size. Co-op performs better than MQTT and MQTT SN as long as its packet size is less than 1024 bytes. For larger packet sizes, transmission time increases for co-op, as can be seen from the graphs. This is due to the fragmentation of larger packets into smaller blocks. MQTT SN and co-op are not suited under limited network conditions. We can conclude that for larger packet sizes, MQTT is preferable over co-op. When it comes to energy efficiency, TCP and WebSocket protocols are unaffected by physical location of servers having different delay or bandwidth characteristics. Co-op, MQTT, and MQTT SN have low energy efficiency due to underlying uh, transport protocols, packet fragmentation, and poor implementation, etc. As as in the performance experiment, co-op's energy consumption increases with packet sizes greater than 1024 bytes. When the packet size is larger than 1024 bytes for MQTT in the Oregon and Tokyo cases, it consumes lesser energy than co-op. For relatively larger packet sizes, MQTT should be favored over co-op. This result is analogous to the one obtained in the performance metric experiments. Resource usage is measured in terms of CPU and memory. Similar to performance and energy characteristics, CPU usage of MQTT SN increases when the client is connected to the local and Oregon server as the packet size increases. Java heap usage, which measures memory, is consistent regardless of physical location of servers for TCP and WebSocket. Co-op requires more memory than other protocols when the client is connected to Oregon and Tokyo cases. Such patterns were not observed in performance, energy efficiency, and CPU time experiments due to fragmentation. The results show that co-op's retransmission mechanism is mainly affected by memory usage rather than CPU usage. The results can be looked at as when the distance of when the distance between client and server increases, the experiments show that MQTT and CoAP protocols are largely affected by packet size. CoAP and MQTT start to fragment a packet from 1 kilobyte and 1.5 kilobytes respectively. If an application utilizes MQTT protocol, the packet size should be up to 1.5 kilobytes for performance and energy efficiency. If a programmer wants to use REST-like APIs, the packet size of CoAP should be less than 1 kilobyte to avoid performance or energy overheads caused by error recovery. CoAP employs a straightforward retransmission mechanism using exponential backoff time on top of UDP, while MQTT relies on TCP error recovery mechanism. Due to poor implementation, MQTT-SN is not ready for real-world mobile software development. TCP and WebSockets often outperform IoT protocols. In conclusion, we can say that the challenges of choosing an appropriate communication protocol for resource-constrained application remains. We have compared the performance, energy efficiency, and resource usages of 5 different network protocols.